So without further ado, I have the pleasure to present David Porfirio. He is a fifth-year PhD student at University of Wisconsin-Madison, and he will be presenting his very interesting work on how to author social interaction between humans and robots. I'm looking forward to learn more about this. So David, when you're ready, you can share your screen.
Sounds good. Yeah, I will begin sharing right now. Okay. And can everybody see the slides? Okay.
Yes, it's perfect.
Cool. Yep. And yeah, just feel free to interrupt at any time. I'm happy to answer any questions. Cool. Okay, so I will go ahead and begin. Yep, I'm very excited to be here and very excited to talk about the main threads of research that I've done so far in my PhD graduate career. And so I've titled this talk Authoring Social Interactions Between Humans and Robots, because most of the work that I've done so far pertains to this notion of authoring. And before beginning, I just want to acknowledge my colleagues and mentors that I've worked with over the last few years, Bilge Mutlu, Aus Albarguti, Alison Sape, and Maya Kakmak. Okay, so when I say authoring social interactions, what do I mean by authoring? Well, in the context of human-robot interactions, I consider authoring to lie at the intersection of both interaction design and programming a robot. Ultimately, a program is designed to coordinate the robot's behaviors and have a successful interaction with end users. And so I want to emphasize right now that my focus is on social robots, or socially interactive robots. And authoring typically involves multiple phases, potentially involving iterative design, specification, and testing stages, in which the design phase can be completed with some authoring tool, which I'll go into in a little bit. And the testing phase would be done with a robot that's available to the interaction designers. And this process would ultimately result in the interaction design being deployed on a robot and interacting with target end users. And when I say target end user, I mean the person or persons that the interaction is designed for. And so every step of this pipeline can be used to ensure that the interaction being designed is of good quality and for getting a pretty clear picture of what the robot will actually do. And authoring tools can help make that happen, often by facilitating this iterative process here, the process of design, specification, and testing. And so I'd like to name a few example. Oops, looks like PowerPoint crashed. Give me 1 second. Sometimes PowerPoint will do that, especially on my Mac.
It happens to the best, so don't worry.
This is the first time that that's happened. Thank you for bearing with me.
You have supporters on the chat, so.
Great. All right. So going back to the slide that I was on, let me just share my screen again. Cool. All right, are we good? All
yes.
right. Okay, so like I said, I'm gonna just name a few example authoring tools here as related work. And this list is non-exhaustive, obviously. So first I want to mention Code 3. And Code 3 is an authoring interface that helps design good robot programs by supporting varying levels of expertise, from novices to experts. And people can design and test their programs in this interface. And then there's also an interface that probably a lot of us here are familiar with, Choreograph, which similarly to Code 3 offers an easy way for novices to program social robots. And then there's an authoring interface which I want to mention that looks pretty different from the other two, called Kiwis, and that stands for Know It When I See It. In Kiwis, a robot demonstrates candidate motions, and a motion expert provides feedback to the robot. And one of the underlying principles here of Kiwis is that the experts need to see the motions themselves in order to help unlock this design knowledge that they intrinsically possess. So why do we need these tools? Why do we need authoring tools? The question is, why are they critical for helping people design good interactions? Well, the reason is that there are various design challenges associated with programming robots. And again, I'm going to be focusing on social robots. And for social robots, well, these robots present a number of unique authoring challenges, such as manipulating eye gaze to manage the conversational floor, hand gestures to supplement robot speech, proximity and locomotion to regulate the closeness and appropriate social distance to end users, and then task-created actions like arm movements to hand items to end users. And these individual behavior modalities then need to be coordinated to create more complex behaviors, such as handing things off to people could involve eye gaze, it could involve robot speech. Obviously, it would involve arm movement, and then there's proximity to the user. And then to add to all of this complexity, collections of these behaviors would need to be arranged into a logical interaction flow, and this would result in a full interaction design. And so the interaction flow would just be the culmination of the decision making that the robot makes within the interaction. And it can address questions like, how should the robot handle different user requests? Or how should the robot build rapport with users over multiple interactions? And it's important to address these challenges, as we're going to see in this video that I'm going to show you here. So I took this video in one of the campus buildings at Wisconsin. And in the video, the robot in the bottom part of the screen has a task to provide information to visitors about events in the building and parking around the building. And so I'm going to play the video right now. And you should be able to hear the audio, but please let me know if you can't.
What information would you like to know? You can say events or parking.
Events.
What information would you like to know? You can say events or parking. I'm sorry, I didn't understand what you said. Let's try again. I'm sorry, I didn't understand what you said. Let's try again.
Okay, so I would describe this interaction as slightly awkward. And it should paint a picture of how, in this case, the flow of the interaction can be the cause of this awkwardness. Because the robot, it repeats the exact same thing it just said when it doesn't understand the user, and it also apologizes on loop when it's ignored by the user. And there's probably some improvement that can be made to the flow here. And so going back to these authoring tools, we need them to help us avoid situations like the one that you just saw. Maybe the issue you just saw was related to the interaction designer lacking the technical expertise to program a good interaction. That's possible, in which the assistance of tools like this could help for novices. Or maybe the interaction designer was a technical expert and they know how to program a robot. But the problem could be an edge case that is easy for the designer to overlook if they don't see it in action. So a tool like Kiwis can serve as good inspiration for how an authoring interface can help elicit this knowledge that's already possessed by the designers. Because recall that in Kiwis, motion experts provide feedback on motions exhibited by the robot rather than programming the motions directly. And so this interface elicits tacit knowledge. I know it when I see it. And so in our case with the awkward flow, if the designer could see the awkward behavior in the robot while they're designing it, maybe they could have prevented it. So we have this potential of authoring tools to provide both knowledge support for designers, in which designers are given knowledge that they don't already know, such as by tailoring themselves to different levels of technical expertise, and knowledge elicitation from designers, extracting knowledge that is already known to them, such as with Kiwis eliciting this tacit design knowledge. And I created a graphic that I'll show in a moment to help visualize the general flow of input and output within the authoring process, and how both knowledge support and elicitation fit into that flow. So for each authoring tool that we build, the pipeline of information will generally flow from the interaction designer to the authoring tool. So the designer provides input to the tool. And then from the tool, an interaction design or a program gets created as output that can then be run on a robot. And as I previously said, the authoring process can help elicit knowledge from the designer, which might come directly from the authoring tool or from viewing the interaction design playing out on a robot. To lend knowledge support to the designer, a knowledge base can supplement the authoring tool or the resulting design that's run on the robot. And I'd like to emphasize at this point that this model is very much preliminary because I don't have all the answers yet. And as we'll see, part of the focus of my research is going to be to refine this model. But we can safely say that the amount of each type of support should be doled out on a case-by-case basis. So as an example of how that applies, Suppose we want to create an authoring tool that hospital staff can use if they want to design a delivery robot to deliver items between areas of the hospital. And so the staff are experts of the context which the robot will be deployed in. So therefore, we'd want to build a tool that can help elicit their contextual knowledge and integrate that into their interaction design. But on the other hand, they might not know how to program a robot. They are probably not roboticists, and so they're likely not experts in how different robot behaviors can be leveraged in order to achieve their task and social goals. So therefore, we want our tool to provide technical and behavioral support. As another example, we have someone else who would be the opposite from the contextual expert, which is the roboticist, like the person shown on the screen. And these people would have more expertise in programming the robots. And so for them, we might want to build a tool that can organize their knowledge and help them leverage their knowledge of robot behaviors, but also provide the support that they need for the context that the interaction will be deployed, the target context. And so the questions that I have in my research, the general high-level questions that are sort of underlying everything that I do is, how can these tools support the design of socially interactive robots by firstly filling in gaps in designer knowledge and expertise, so providing them knowledge that they don't have, but then also helping elicit their knowledge that they already possessed and assisting with the integration of this knowledge into their interactions that they design. So in the remainder of my presentation, I'm going to talk mostly about the work that I've done so far, but I do want to touch upon some work that I'm currently doing. And then at the end of it, I'll end by discussing the implications of this work and offering some high-level plans for future work. Right, so let's start by talking about past work. And I split my past work into 3 different research threads, and I will go back to this slide in a moment. But I first want to frame these threads within the dimensions of knowledge support and elicitation that I already mentioned, and I find it useful to do this. So knowledge elicitation is on the vertical axis, and increasing upwards, and knowledge support is on the horizontal axis, increasing to the right. And the first 2 tools that I'm going to talk about, I call Rover and then transforming robot programs. And I classify these as knowledge support tools. They offer knowledge to people designing interactions. And they provide and integrate this knowledge because it's not necessarily known to the interaction designer at design time. So I'll start by talking about these research threads. And I will begin with Rover. So with Rover, the first research thread investigates how authoring tools can assist designers creating interactions that adhere to social norms. And the culmination of this work is a keyboard and mouse authoring tool, which I've already named. It's called Rover. And so going back to our authoring pipeline, Rover mostly focuses on the design specification phase of the interaction. And to enable interaction design, it allows people programming the interaction to take a set of behaviors, like the 5 behaviors that you see on the screen right here, and assemble and parameterize them in what we call the design pane. But the primary novelty of Rover comes from its ability to provide feedback to designers based on whether their design satisfies a set of social norm properties. And for us, the set of social norms that we check interaction designs against comes from the literature. And I've just provided 5 examples of social norms on the screen right here. There are some fairly simple ones, like the robot should issue a greeting and the robot should say farewell. But then there are also some more complicated ones that are up for a little bit more of interpretation, like the robot should coordinate its gaze with its task actions, or the robot should adhere to conversational turn-taking norms, or the robot should not disrupt the human's workflow. So what we do then is we express norms in what's called linear temporal logic, or LTL for short. And LTL is just a representation that enables for computational analysis of a program. So an example formulation of the property, the interaction must end with a farewell. We can formulate that in LTL as the following. Starting at the beginning of the interaction program, at some future point of executing the program, the interaction must end. And at any point when it ends, the robot must be saying farewell. So then what happens next in the back end of Rover is, given a social norm in LTL in an interaction design created by a user, we perform what's called formal verification, in which the interaction design is checked to see whether it satisfies the social norm. And if the social norm is not satisfied, we return feedback to the user saying, hey, this social norm was not satisfied. And as you can see here, when the designer completes an interaction with rover, when the designer completes an action with rover, the feedback pane updates with the social norms that have been violated. And we provide a little blurb describing the social norm that was violated. And we evaluated rover with a small comparative user study. And in this evaluation, we tested the effects that feedback from formal verification has on the interaction design process. We found that participants who received feedback more accurately perceived errors in their design and also found it easier to find and interpret social norm violations. And so I'm just briefly touching upon the evaluation here before moving on. But that is my quick overview of rover, which just to recap, centered around providing knowledge support. And the form that the knowledge support took was a database of social norm properties. I want to talk about the other project that I did that centered around knowledge support. We called this project Transforming Robot Programs Based on Social Context. Going back to our authoring pipeline, this particular work focuses on modifying an interaction after it's deployed. And as you'll see in a moment, I wouldn't so much consider this to be an authoring tool per se, but instead I would consider it to be an authoring support tool. So just as a recap, going back to this interaction that you've already seen, let's say that someone actually designed this by hand and they could have designed it using a tool like Rover. And we already know that this is an awkward interaction because the robot repeatedly lists its behaviors when it doesn't understand the user, and also it apologizes on loop whenever it's ignored. And so we can imagine that the underlying program guiding this interaction looks something like this, a state machine. And as I already said, it could have been designed with a tool like Rover. And you don't have to understand most of what's happening here, but let's just say that most of the problems arise from the components of the program that I'm going to highlight in orange. So in this section, the robot is doing the repeated queries to the user. And then in this section, the robot annoyingly apologizes to the user when they're ignored. And this information can be repaired by transforming the structure of the program or its control flow so that the robot doesn't do either of those things. And this, in green, I've just placed one possible repair. Doing these repairs by hand is possible, and that could be done by observing the robot interact with users and then noting what needs to be repaired and then doing it yourself. But the goal of this research thread is to automatically perform this repair process. And we do that by collecting user feedback as the robot is interacting with end users. And so, like I said, we deploy an interaction design program on a robot. And then what we do is we record execution traces of users' paths through the interaction. And then users are prompted to rate the quality of their experience. After that, once we're given a set of user-rated execution traces, we search for a new robot program that accepts only a subset of these traces in order to maximize user experience. So going more into detail of that, essentially, as an example, if one positively rated execution trace exists, and then another negatively rated execution trace exists, we search for a new program that only accepts the good trace and does not accept the bad trace. And so similar to Rover, we ensure that the modified interaction design adheres to a set of baseline linear temporal logic properties. We want to make sure that repairs don't produce a nonsensical interaction with the robot. So we have the repair process adhere to a set of rules. And the final part of our approach is that we just repeat this repair cycle over time. So at each day of interacting with users, the robot will collect new user input and match those to the execution traces that the users experienced. And then at the end of the day, the robot will search for a new interaction that maximizes user experience. And then it will repeat that over the course of multiple days and gradually improve the interaction over time. And we evaluated this approach with a field experiment. And in the field experiment, we deployed robots at the welcome desk of a campus building, the campus building that you saw in the video. One of the robots we adapted over time based on user feedback, and the other robot, we had its interaction program remain constant. And shown here on this slide, these are the user feedback results of the transformed interaction design when no further modifications to the design were made. So we made sure that in the last few days of the field experiment, we stopped modifying the robot's program, and then we collected user experience. And our results show that user feedback scores for the transformed interaction are significantly higher than those of the original interaction. Okay, so ending the two research threads that really focused on supporting designers with knowledge. We have Rover, which, as a recap, we supply designers with a set of context-free social norms. And then with the approach to transforming robot programs, we support the authoring process by shifting responsibility of knowing anything about the context away from the designer. So the designer, when they're creating an interaction, doesn't necessarily need to know very much about the context, because the goal of this transforming robot programs approach is to fit it to the context post-design. And so with this, I'm going to venture into the knowledge elicitation that I talked about with the third work that I'd like to discuss.
David, I'm sorry to interrupt. There is
Yes.
a question in the chat that asks, Leon Watts asks, what is the scale on the user feedback graphs?
The scale on the user feedback graphs, this one right here. This was, we did a 7-point Likert scale, I believe with 4 questions, basically. Ooh, I would have to look back to know what the exact question was, but it was basically asking, how is your experience interacting with the robot? This result actually was, so these results here were 7-point Likert scale. This result here was, I believe, just a 3-point Likert scale. Was your interaction good, neutral, or bad? And so this is, these are the scores that also served to improve the interaction over time. And then we also use these scores to assess how successful our approach was. Okay. All right. So, so I'm going to venture into knowledge elicitation with the third work that I'd like to discuss. So here we go. As you'll see, synth's contributions primarily revolve around design specification. And so this is what the design interface of synth looks like. But the graphical user interface is not the focus of designing an interaction with synth. The focus is having design teams role play or act out examples of how an interaction should play out between a human and a robot. So synth is recording these design teams as they perform their interactions in the background. And it uses microphones to capture designer speech and armbands to capture designer gestures. And the core premise of synth is really about utilizing these designer demonstrations to elicit knowledge. Because when designers role play an interaction, they're actually undergoing a design process called body storming. And with body storming, we can unlock our intuitive knowledge about social interactions to form ideas about how we should program our robots. And this is done under the premise that we know more than we can tell, which sounds really similar to the idea of Kiwis, the related work, the idea of I know it when I see it being critical for design. So going back to our design sessions, after synth records speech and gestures, the speech and gesture streams are labeled and overlaid in order to create an execution trace of the interaction design. And the execution trace looks like this. And it simply contains the sequence of events within a demonstrations that designers provided to synth. And after performing a demonstration, the trace is then presented to the designers so that they can either accept it or reject it. And they also have the opportunity to correct any mistakes that synth made by editing it manually. So, given multiple input demonstrations culminating in execution traces that have been provided by designers, these execution traces may vary in both length and content. Our tool synthesizes a full automata representing the interaction design. And this automata accepts all input traces provided by designers. And after designing an interaction or during designing an interaction, the design teams can test their creations on a robot. All right, so we evaluated synth with a user study in which we asked 12 design teams to create interactions using synth. And we found in general that, so this is qualitative feedback. We found in general that designers tended to bring in outside ideas into their design, but also integrated design feedback from synth into their creations as well. And we also found that demonstrations tended to be written out before being performed, and that the iterative design process facilitated by synth helps solidify people's mental models of the capabilities of both the authoring tool and the robot. Furthermore, I found this to be very interesting. Participants thought that acting felt artificial, and this actually mirrors past work, past findings of the body storming design method. Role-playing does feel artificial to people sometimes, or awkward. Participants relied most heavily on dialogue with each other in their performances, as opposed to relying heavily on gestures and props. Okay, so going back to our graph, the question is synth successful at eliciting design knowledge? And I would say it appears so, given that a core finding that we found is that designers integrated outside knowledge and feedback into the design process. But now, so what is the role of embodied design in facilitating this knowledge elicitation? And I do think that there needs to be some future work to investigate this further. So I would get into that with some of my future work. And that concludes the work that I've done in the past. And I'm going to revisit this a little bit later on in the talk in order to fit it within my model of knowledge support and elicitation. But first, I'm going to briefly touch upon my current work. And this is work that we've just wrapped up, completed, and it's called Figaro. It is a tangible tabletop human-robot interaction programming environment, and it is somewhat of an extension of synth, as we're going to see, because designers are still demonstrating execution traces of how an interaction should play out. And this work, Figaro, also focuses on the design specification stage. And the idea behind Figaro is that we want to provide people with a set of simple manipulations that can map to complex interactions in the real world. And so this would connect design actions directly to the actions of the robot. So if you move a figurine from one end of the tabletop to another, the robot will move to a different room, as an example. And the world on the tabletop does not match the real world exactly, as you can see on the screen here. We opted instead to abstract the real world into a higher level virtual representation. And this is the representation that the figurines move around in. And we also added tangibility to the figurines such that actions enacted on the figurines map to actions on the robot. Okay, so now I'd like to get into the nitty-gritty of how Figaro works. So this is what to start with that, this is what the design pipeline within Figaro looks like. First, users would draw out the physical layout of their target environment, and they would do this on an external tablet interface. And this is another reason why we opted to go for abstract representations of the real world, so that users could draw out what they expect the real world to look like. So then users would demonstrate scenes of an interaction, similar to with synth, but with figurines on a tabletop. And finally, users can deploy their interaction designs on a robot. Okay, so let's take a look at what demonstrating a scene looks like in Figaro. I'm going to play a video here. Robots say, "Hello." Humans say, "Can you please show me to the conference room?" Robots say, "Yes." Okay, so that is just the example. When demonstrating, designers receive feedback from the interface on the proximity of the robot to other actors in the scene, as well as the speech recognized by Figaro. And if attached to a joystick, the designer can make the robot point. We'll play that right now. And this maps to a real robot. We used a Temi robot for deploying interactions with Figaro. And on the Temi robot, which doesn't have any arms, a point behavior would just be the robot twisting its body and nodding its head. Whereas if we had deployed it on a robot with arms, the point behavior would obviously be the robot pointing using its arm. So the designer can also make the robot tilt its head. And on the Temi robot, that just looks exactly like that. The robot is tilting its head up and down. And also, the designer can make the robot wait for something to happen. So combining all of these features, demonstrating a scene involves coordinating figurine movement, manipulations, and designer speech. And the movement, position, orientation, and actions, all recorded by Figaro, are used to then assemble an execution trace of the scene, which is very similar to what we did with synth. And so given a set of execution traces, just like synth, Figaro will create a full interaction automata. And going back to our graph, the question is now, where does Figaro fall? So I do think that there needs to be some additional work to investigate this. But for now, I'm going to place Figaro on the knowledge elicitation category, and we can call that my hypothesis for future work, because its purpose is really to situate people physically and also within the flow of an interaction, bearing in mind that with all of these works, an added benefit is to support non-technical experts in the programming process. And so, bearing in mind that with all of the works that I've discussed so far, there is some knowledge support that is happening as well. Okay. So that concludes the main threads of research that I've done up to this point. And so I want to ask where this leaves us. Well, with 2 out of the 4 tools that I talked about, these tools provide knowledge support. One of the tools provides support to the designer through a database of social norms. And the other tool, the program transformation approach, leverages contextual knowledge, which is in contrast to the other tools. But this is done only after the interaction has been authored, not during the authoring process itself. And then going back to the slide, the other 2 out of the 4 tools probably fall more under the knowledge elicitation category, where synth uses its interface to facilitate body storming. And the goal here is to elicit tacit design knowledge. And Figaro physically situates people within the interaction flow. But in both of these systems, designers are creating interactions for a general interaction context, and they're not integrating highly context-specific knowledge into their designs, which leads me to where I'd like to go next. And I'm only going to, I'm going to try to briefly touch upon this so that we can have time for discussion and questions. I would like to focus on how can human-robot interaction authoring tools supply contextual knowledge during the design process, and then also how can they elicit contextual knowledge during the design process. And I think that one way to begin eliciting contextual knowledge is to begin shifting focus to end user programming. So whereas we're currently focused on people designing interactions using, like for instance, a graphical user interface, but then these interactions would be deployed for someone else to use, for some other target end user. We can start thinking about the users of these robots themselves and how they might be able to supply the knowledge of their own familiar interaction contexts. So just as an example, let's say that we have a Temi robot here that has a native delivery function in which it's able to take something from a kitchen and bring it to someone else in the house. An end user might want to use this delivery function to bring items to a dinner table during a dinner party, but only when observing the robot in action may the end user realize that the specific speed of the robot needs to be different than the original speed the robot is programmed to perform, especially if it's carrying food and drinks. Also, the robot should approach individual guests at the table instead of just approaching the table in general. So this would be so that guests don't have to get up and each of them fetch food from the robot. And then finally, the robot might, the end user might want the robot to extend its delivery function to take back dirty dishes. And so this is where end user programming in situ can benefit, because only the end user might know this contextual design criteria. And only by observing the robot in action may they realize this. And so I'm going to skip over this slide in large because I do want to give time for discussion and questions, but for supporting knowledge, for supporting contextual knowledge, we might begin thinking about interaction authoring tools that integrate knowledge from different experts, similar to an existing tool that already has been worked on called Foundry, in which the input from multiple experts is leveraged to create a mobile application. Experts that are contextual experts can combine their knowledge using from robot behavioral experts and from technical experts, such that an interaction design can be created by leveraging all of their input. So I'm going to end my talk now. I just want to revisit this model very briefly. It's useful for explaining how existing tools support or elicit knowledge, but at the moment, it doesn't answer how new tools can be constructed or how they should be constructed. So for instance, we'd like to answer questions like how should knowledge elicitation be leveraged to create a new human-robot interaction authoring tool, using, for instance, the domain expertise of the designer, or based on whether or not they're a target end user of the interaction. So these are types of questions that we would like to answer using a model like this. That concludes my talk. So I am excited to answer questions about it and begin the discussion.
Thank you, David, for this very interesting talk. So we can start our Q&A. Anyone from the audience with a question?
Yes, if possible, I would have a question. Well, good evening, everyone. Thank you, David, for the presentation. It was very, very interesting. My question is the following: do you think there is potential for these authoring tools in human-robot collaboration, where also a physical interface with the user is needed on top of the cognitive one?
Like programming by demonstration sort of thing?
So okay, okay, but what? Okay, so now, yeah, I know learning from demonstration, but what? I mean, do you think there is potential? I mean, how could these authoring tools improve this the learning from demonstration, for instance?
Yeah. Right. I do think that there is a large potential, and already many existing authoring tools that are geared more towards robots for collaboration. I think some of the benefits that we see for social robotics could be seen by applying authoring tools within collaborative robotics, such as the ability to visualize complex interaction flows, for instance. I think that there is also an added benefit that we would not see within social robotics as much, which would be the ability to integrate tangible or utilize tangible design interfaces as well, such as for programming by demonstration, which possibly you would not see as much use for in social robotics if the social robot is not meant to manipulate objects or interact with the user in a tangible way. Is that answering your question, or is there something that you think I could focus my response a little bit more on?
Oh no, I mean, I guess it's your, as you said. I mean, yeah, social robotics is not meant to, yeah, to consider physical interaction. So yeah, I was curious to see how this thing that is not meant for physical interaction could be extended to collaboration. But yes, thank you.
I think one thing that one area that authoring tools could really shine in for collaborative robotics is physically situated designs, physically and temporally situated designs, in which there might be a set workspace that the robot is placed in, and the authoring process could potentially be the same location as the target interaction context. And so a design tool for collaborative robotics could really kind of hone in on that in situ authoring benefit, which is, I think, a little bit more of a challenge, often more of a challenge in social robotics.
Mm-hmm. So by physically and temporally situated design, what would you mean exactly? I mean, do you mean the actual experimental settings into industrial environments? Is that what you mean?
If the authoring process takes place within the actual setting that the interaction will take place, yes, that is what I mean. If the authoring process does not take place, then I think performing in situ design would have the same challenges that we see for many social robot applications.
Okay, thank you for the answer.
David, can I ask you to stop sharing your screen so that we
Sure.
can see each other's?
Okay.
Thank you.
Hey, David, this is Ross, if I could jump in with a question.
Hi, Ross.
Hey, David. First off, great talk. I remember we were talking about this on a plane to Korea last year, back in the day. So it's awesome to see your cohesive vision, all in one presentation. This is fantastic. I did have a question about the role of the programmer. I know you mentioned it kind of in the beginning of the talk, and I felt like it was kind of touched on that slide 100 near the very end there. So in our experience in industry with both voice assistants and social robots, more than 60% of the time is spent for the content creator, the interaction designer, coordinating with the programmer on sort of like their own, the social constraints that need to go into the code of what the programmer is doing. And oftentimes the flow that they have, there's trigger, which is usually, what a user is saying. And there's an end response. And in between there is what they call fulfillment. And that's usually this black box of code that actually starts incorporating the social elements as well. Could you talk at all about where you feel the programmer fits into the workflow of the interaction designer in this?
Yeah, I think for a lot of what I talked about, these tools would sort of automatically, would simplify the programming process for the interaction designer themselves, right? Although I think that that would mostly apply to the specific set of tools that I talked about. I can envision scenarios where it is actually quite important to separate out the interaction design process from the code itself, especially when we get into needing to program some finer grained detail of the interaction, where, for instance, with Rover, we just had a set of parameterizable building blocks. Well, let's say we wanted to create new building blocks. We might want to leverage the expertise of someone who's actually able to do that. And I think that's kind of what I would hope to get into with some of the final stuff that I talked about, in which we have an authoring tool potentially which could integrate that technical knowledge for highly context-specific interactions, in which a set of building blocks provided by an authoring tool might not suffice. So that's kind of where I would see that high level of technical expertise coming into play. Yeah, I think it has been, for me, a large challenge to attempt to break free from the constraints of a finite set of building blocks.
Gotcha. And if I could add one more thing, because we're talking about teams here, interaction designers and programmers, who do you see are the ones within that team who are specifying the social norms or other norms that might be about the character of the robot?
That is another really good question. So just to recap, with Rover, the people specifying the social norms were other researchers. We grabbed the social norms from the literature. And so I had hoped to mention, but didn't, that some future work we would like to perform in the realm of Rover is exactly to address that question. Where are these norms coming from? I think I could see them coming from the interaction designer, but we would run into the same challenges that I discussed, where the designer themselves are not immersed necessarily within the context that the interaction will be deployed. My solution, which I would be going forward with, is to place that responsibility on the end users. Although I could also see other solutions that I have talked about with other people in the past that involve crowdsourcing, or that involve just over time compiling a source of, compiling a database, sort of like an open source database of social norms. There are clearly challenges with that approach, especially given the fact that there's an infinite set of contexts out there. So how can we enumerate social norms that apply to all of these contexts? And I think that's kind of why I'm leaning more towards placing that responsibility on the end user.
David, I think we have a question from Amanda.
Okay.
Oh, yes, thank you. So I was just wondering, I mean, my work is all with kids and, you know, kids using robots to learn. And it just seems like this would be a really great teaching tool. Have you ever used this in an educational context?
We have not. However, with Figaro, with the last tabletop design tool that we came up with, a lot of the supporting literature for Figaro is with educational applications and the benefits that it has for, well, the benefits that tangible programming has for teaching kids how to program, getting kids to collaborate with each other. These are all things that I would need to, I can't really speak from the perspective of an expert, obviously, on the benefits of this for children. But there is work at Wisconsin that is happening in our lab within the educational domain, and I think it would be useful to begin forming these collaborations. I think there are clear benefits that could be gained from using these types of tools. And just, yeah, like I already said, just a vast amount of related work within tangible tabletop designs and education.
And just going back to the social norms discussion, I mean, I work in particular with kids who are underrepresented, typically in STEM. So I work with young girls. I work a lot with young girls of color, and you know, those are a lot of the conversations we have. That we have this robot that was maybe programmed by someone who's not the same as them, and then it behaves in a way that isn't really you know, according to their norms. So I think that would be a really great education tool, and it just looks so cool to me. So thank you.
Yeah, I agree. I would love to see it in that being used in that way. Thank you.
I have one question too. Hey David, a great talk. Finally got to see your full talk. I have one question about your insight on how to balance the expressivity versus ease of use trade-off in domains of the programs or types of programs that you have seen people doing. For example, I see this sort of the formal verification, like all these assistive tools that we end user programming people build could also choke or constrain the user, which limits their creativity, the spark. Like they don't use these tools because they just want to write down some open-ended things. And maybe in similar line, where maybe another way of asking the same thing is, where do you see the most variance of contents generated by using such tool comes from? Like, is it the order of the presentation of certain content? Like, so with all these assistant, what would be the core content the creator will be focusing on? Yeah.
But so by core content, if I said it was the sequence of robot behaviors, would that answer your question? I have a lot of thoughts about this, but not so many conclusions. What you had mentioned earlier on in your question about expressivity, that is the problem. So with Rover, maybe people could see this when I talked about Rover, but it was heavily inspired by Choreograph. And I think Choreograph, as the authoring tool that is packaged and shipped with the Aldebaran robots, does balance the expressivity and the ease of use, sort of in a similar way that also Code 3 does, by basically tailoring different components of the interface to different levels of expertise. And so I think that's one way of doing it, but that also leads to a fairly complicated design tool that just offers so many different pathways to program robots. And so that's fine. It would be an expert tool. If we're thinking more about novice tools for end users to sort of get up and going, just expressing to a robot in the simplest way possible what they want it to do, but also as expressive as they want to speak to the robot to specify these behaviors. I think the target input modality that we would want for end user programmers, in my view, and I would love to hear other people's opinion on this, is the verbal input modality, because it's simple for people to express. However, and it is very expressive. You can express a lot of detail with it, but it is so difficult to understand and parse correctly into a program that, when you have that level of expressivity and simplicity of use, it just becomes a lot more difficult for the creation of an authoring tool to handle that. So yeah, like I said, I don't have answers for that, and so that's why I'm kind of starting to ramble about that. I would say that with the tools that I discussed so far, the most successful one that balances expressivity and ease of use would be Figaro, because Figaro offers multiple input modalities, position, movement, orientation, as a finite set of actions that the robot can perform. You can perform multiple demonstrations, but there are still limitations, like you can't express the timing between different behaviors that the robot could perform. At the moment, you wouldn't be able to express these different parameters for how the robot should approach people, or you could express that with Figaro, but it wouldn't necessarily be at the moment compiled down into the robot program. So that's my non-answer. It's a huge challenge.
David, there is a question from Leon. Leon, sorry, I missed your raised hand.
Don't worry about it. I said I was going to be cheeky earlier on, and I'm not being cheeky at all, am I? Yeah. So thank you very much for the talk, David. There's a lot in it, wasn't it? 3 different approaches to thinking about how to support interaction designers in realizing their dream one way or another, wasn't it? Or helping another person, I think in your terms, a domain expert, to realize their dream. And that distinction between the kinds of knowledge that could be you could assist with, I think it's quite a good distinction to make. It seemed to me that the one way which you called elicitation, it's reminiscent to me of heuristics to support interaction designers in like regular interactive systems, in making sure they haven't missed anything, which is very easy to miss otherwise in working through the design. So I think that's possibly a connection that would be useful to you to think about that. So the sort of thing that pops up if a designer has missed a thing is described as a usability bug in a relative, in the kind of related world. And that's quite different from, let's say, something like a semantic gap in the whole interaction design concept, which seems to be so if there are no usability bugs, a person can use it, but it might have no value at all to them. And that's where your domain side, the domain side of the world of your equation comes in. And so perhaps especially because you're talking about authoring tools, I was wondering whether or not you considered more overarching concepts in the development of a story that might integrate the lower level behaviors that you have described. In the regular interaction design world, we talk about scenarios as being ways of capturing domain relevant information in sequencing and inclusion of operations and events that might be relevant. And also storyboards, that they're things that can be developed.
Yeah,
I guess you've heard, you know about those. So I guess there's a interesting distinction, and I wondered whether or not you think there might be some role for scenarios or incorporating scenario development in an authoring tool to contextualize the way that I forgot what the phrase you was now, the sort of component behaviors, the base behaviors that exist, how they might be brought together.
Yeah, it seems so natural that that would be a method of expressing robot behaviors using these design tools, that is storyboarding and scenarios that exist for robotic and non-robotic systems alike. And I think that's a fantastic idea. And I think the benefits of that would be, in my view, and I would be interested in hearing your thoughts about this as well, similar to synth. This is just what I'd like to relate it to for the time being, in that we have these designers who are they are external from what the interaction is being designed for, but the purpose of the tool is to just extract as much knowledge from them as possible. I think it would be an interesting direction to take, and also possibly technically challenging, in that a lot of what we do is would need to extract this information from the storyboards or from the scenarios, like for instance, the textual description, into some, possibly a prototype that could then be refined further. Yeah, I think that's a really interesting direction. And I can absolutely see.
Thank you. Yeah, so if one was to think about a design team, so a multidisciplinary design team that would involve technical people who are doing the ROS stuff, and interaction designers who are kind of constructing flows, as you say. I quite like that idea, actually. Flows that could be that you know are technically valid, that they could be realized in the robots, and then others in the domain who were equipped with tools to bridge their understanding of the domain with the interaction designers. Then what might happen is that the interaction designer would realize there is some constituent behavior that's required and deliverable, but doesn't yet exist in the catalog of behaviors the robots can perform. So it's something. Well, this is me speculating. It could be a stimulus for expanding the repertoire of behavior in the robot. And so adding value to what that system could offer in other domains as well. So although on the face of it, it's coping with a very specific kind of problem, which is how do you translate the demands of particular domains into well, it's, as you say, interaction design and realization of a robot that can work well there. I think it could have a role to play in building up a catalog of realistic behaviors as well. Realistic is the wrong word. Deployable and potentially valuable behaviors.
I agree. Yeah, and I think that would be one of the threads that could be extended from this multi-domain expertise scenario that I touched upon in the last few slides of the talk.
Okay.
Yep, I think that, you know, to really begin to realize the potential of these tools that I talked about in real domains, it is necessary, I think, to address the creation of these building blocks. And even if the building blocks aren't created to be specific to a particular domain or context, at least realizing what the tweakable parameters need to be in order for someone to easily achieve that domain fit themselves.
Yeah, right. Thank you very much. I'm going to stop now because otherwise I'll be hogging the floor too much. Too cheeky.
I'm loving this discussion. I have a lot of questions myself, but we're reaching our time, and I need to make some announcements and finish this session, unfortunately. However, we have a channel, in a Slack channel, where we can continue this discussion, and it was just created, so you can join there. So perhaps I'm going to share my screen. Sorry. Okay, sorry for the delay. So before we go, there are a few things I would like to say. Talking Robotics is going to pause for 3 weeks due to the festivities, but we are back in January with a great topic presented by Barbara Bruno that we talk about culturally aware social robots. So stay tuned in our social media for more details on this and upcoming talks. I think we'd like to thank HoboHub for the partnership, and we wish you well, wish you happy holidays, and enjoy your time with your families in the safest way possible. Thank you, David. I loved your talk and this topic. I hope we can continue this discussion later.
Yes,
Thank you, everyone.
Thank you for
see
the
you next
discussion,
year.
everybody.
Thank you, David. Bye-bye.
Bye.